Let's see. So problem one, you got these three vectors. A is 1, 3x. B is x, 4, 3. And C is actually, doesn't have any variables in it. It has, yeah, okay, sure. Yeah. If you guys are asking questions in the messages, I will get to them in order. So yes, you can be assured that your questions will get answered. C is -1, 0, 3. And part B asks, if x equals -2, find a unit vector that points in the same direction as B. Okay, so if x is -2, then B is the vector -2, 4, 3. And the unit vector that points in the same direction is just that vector, B, divided by its own magnitude. So that's our unit vector in the same direction. And to calculate that, it's going to be the vector -2, 4, 3 divided by, or really when I'm dividing a vector by a scalar, I really don't love writing like the entire vector divided by it. I just feel like it looks weird. I would probably write 1 over the magnitude. So the magnitude of B is the square root of -2 squared plus 4 squared plus 3 squared, which I believe is the square root of 29. So the unit vector in the same direction as B is 1 over the square root of 29 times -2, 4, 3. Or you can write it as -2 over root 29, 4 over root 29. You shouldn't have to rationalize that, but I guess someone could expect you to. I doubt it, though. Let's see, part C. Explain whether the following expression is meaningful. Okay. Question is C dotted with A plus the vector B. Okay. So this is definitely not meaningful, and here's why. C dotted with A, this is a scalar. Or a constant. It's a real number. And a real number, so let's say C dotted with A, if we plugged in -2 for just 1 second, C dotted with A would be -1 plus 0 minus 6, if we're using the value of x given. Although you don't have to, but I'm just trying to give an example. So -1 plus 0 plus -6 is -7, plus the vector B is -2, 4, 3. And we can't add a scalar to a vector. So no, this does not make sense. We can only add vectors to vectors or scalars to scalars. We can't add scalars to vectors and vice versa. It's a fair question. Okay, so that's short test problems 1B and 1C. Let's move on to the next question someone asked, which is number 1 on the practice problems that Dr. Burke posted. Sure, I had that up, but I think I closed it. Let me grab it again. Of course, you're all very welcome. So problem 1, oh yeah, problem 1's a good one. Hopefully you all noticed, and I did just do it in the last hour, that I did post video solutions to problems 1 through 8 for the practice final. I posted. I will do number 9 after class today, but those are up there and you can look at them anytime. Also, before I forget, if you have not already, please do fill out this attendance form. Thanks. All right, so here's the question. We want to write this integral from 0 to 3 of e to the -x squared. Oh, I'm sorry, there's -x over 2 dx as a limit of Riemann sums, taking the sample points to be right endpoints. Okay. So the whole idea here is we want to write this as the limit as n goes to infinity of the sum from, I don't remember if she used I or K, it doesn't really matter, but I feel like she used K, but it might have been I. K equals 1 to n of f of x sub k delta x. That's the very general format, where x sub k is the right endpoint of the kth interval. Delta x is b minus a over n. And f of x is just this function over here. So that's your f of x. And there's our a, and there's our b. So we pretty much got everything we need. So to find delta x is going to be 3 minus 0 over n, which is just 3 over n. It might help to write out the number line to see what x sub k is. There is a formula for x sub k. If you can remember it, x sub k is just a plus k times delta x, which in this particular problem is 0 plus k times 3 over n, which is 3k over n. But you might not remember that. So if you don't remember that, the way I recommend to figure out what x sub k is to draw a little picture. So I'm going to draw the number line. And I'm going from 0 to 3. And you get your function e to the negative x over 2. It probably looks something like this. I don't really care what it looks like. I'm just trying to give context. What's important here is that we know that we are calculating this interval, or at least the idea behind this limit of this Riemann sum is that you're calculating the area under the curve by adding up all the rectangles areas and then taking the limit as the width gets really small. So like we've got this rectangle, and again, we're using right endpoints. So look like this, and this rectangle. Again, you really don't need this picture. I'm just trying to show you one specific thing. Let me go out of the ways. Okay. So the thing I want you to see is that each of these rectangles, the width of each of these rectangles is delta x, which is 3 over n, right? There's n rectangles. The entire length is 3. So if there's n rectangles and they each have equal width, each of their widths is 3 over n. All right, so then for this first rectangle, the right endpoint, which I'm going to call x sub 1, is 3 over n. Okay. And I should say, right, this left endpoint x sub 0 is 0. For the second rectangle, the right endpoint, I'm gonna run out of room here, so right up here. The right endpoint x sub 2 is, well, it's 0 plus delta plus another delta. So it's 2 times 3 over n. And for this third rectangle, the right endpoint is x sub 3. It's 3 times 3 over n. It's 3 deltas. And I think you can see where I'm going is that in each of these rectangles, the right endpoint, x sub 1, x sub 2, x sub 3, is just that number times your delta x. So that if you go over here to say the kth rectangle, the right endpoint, which is x sub k, is k times delta x, which is 3 over n. So your x sub k is 3k over n, just like we saw up here. That's what's going to go in there. So here's what's going to happen. X sub k is 3k over n. Delta x is 3 over n. And f of x is e to the negative x over 2. So this is kind of the important part. F of x is e to the negative x over 2. F of x sub k is e to the, we have to replace x with x sub k, which is 3k over n. So it's e to the negative 3k over n over 2, which I know is a little unwieldy, but that's what we've got. You could simplify that if you really wanted to, but I don't think that's the point. So then we can rewrite this limit as the limit as n goes to infinity of the sum from k equals 1 to n. F of x sub k is this e to the negative 3k over n over 2. Times your delta x, which is 3 over n. And that's it. So for this sort of problem, if you're given an integral and you have to write the limit definition of the integral, it's always going to be the, and you're using right endpoints, it's always going to be the limit as n goes to infinity of the sum from k or I, whatever you're using, from equals 1 to n. And then here's where you actually have to do the work. Your delta x is this minus this divided by n. Your function, f of x, is just whatever is in the integral, but then you have to replace x with what x sub k is. And x sub k is where you have to do the work of figuring out, okay, x sub k is this a plus k times delta x. So that's how you do one like that. Is it different if you're using left? It is slightly different, yes. So the difference if you're using left endpoints is, and so there's kind of a cheater way to say it's different, and there's kind of the way she would probably expect you to do it. So the what's the word I'm looking for? The still correct way, but not exactly what she probably would want way, would be to say, well, using the left endpoints, I would do this, the limit from n as n goes to infinity of the sum from, well, instead of using, right, k equals 1, k equals 2, k equals 3, I want to start at k equals 0. So I can do k equals 0 to n minus 1 of f of x sub k delta x. And then you have the same thing. So it would literally be the same thing, except you start at 0 and end at n minus 1. But I don't really think that's what you would actually want. Although she'd have a hard time saying you were wrong if you did it that way. She'd have to be very specific in her wording to make you do it the way that I think she would want you to do, which is the following. So to use left endpoints, what we're going to do is the limit as n goes to infinity of the sum from k equals 1 to n of f of, so for the first rectangle, the left endpoint is x sub 0, the right endpoint is x sub 1. For the second rectangle, the left is x sub 1, the right is x sub 2. For the kth rectangle, the right endpoint is x sub k, the left endpoint is x sub k minus 1. So that's going to equal this same integral. Sorry, it's not the integral, it's the same limit. So it's the same limit, n goes to infinity, of the sum from k equals 1 to n. But now instead of f of x sub k, where x sub k, right, is 3k over n, x sub k minus 1 is 3 times k minus 1 over n. Or if you prefer, right, you're just going back one. So it's 3k over n minus a 3 over n. Same as that, just written differently. So that's what's going to go in for your x, right there. So it's going to be kind of gross. It's going to be e to the negative x, which is your x sub k minus 1. So that's going to be 3 times k minus 1 over n over 2 times 3 over n. That would be the only difference, is that your k's all get replaced with k minus 1s. It's not that bad, right? So all I'm doing is I'm taking the same thing, and that k, I just replaced it with a k minus 1. So left is not much worse, but I really would have a hard time imagining her asking you left, since we almost completely focused on right endpoints.
I have a question. So for the left endpoint, is it always like minus 1?
Yeah, it is.
Okay. So like even in any like finding the limit definition of an integral, the left endpoint, it would be like with minus 1.
Right. Yes.
Okay.
So literally the very general, right? So this is literally the limit definition of the integral using the left endpoint, and the only difference between using the left endpoint and the limit definition using the right endpoint is your x sub k minus 1 versus your x sub k. Everything else, totally the same. Okay, someone else had asked about.
Sorry, what about the midpoint of it? What did she ask about, like that?
So the midpoint would be even grosser. The midpoint would be, so you have to take the midpoint of those. And so the midpoint of the left and the right endpoints is the average. So if you wanted to do it that way, here's what it would look like. Midpoint would be the limit as n goes to infinity of the sum k equals 1 to n of f of your midpoint, which is the average of x sub k and x sub k minus 1. So still essentially the same thing, except that now it's going to be the limit as n goes to infinity of the sum from k equals 1 to n. So my function is e to the negative x over 2. So it's e to the negative stuff over 2 times your delta x, where this stuff here is the average of your x sub k and your x sub k minus 1. So it's literally, or let's do it like this. It's literally this plus this divided by 2. So 3k over n plus 3 times k minus 1 over n, all divided by 2. That would be the midpoint. Other questions about this? Okay. So somebody asked for an integration by parts problem. Let's do, sure. I got a couple, and that's the last question that anyone is asking. So if you have other questions, you should. Let's say I want to integrate, I don't know, natural log of x over x to the 4th from 1 to 7. Okay. It could be u sub, it could be integration by parts. I'm always going to think about u sub first. So think about u sub, I would try letting u equal the natural log of x. The problem there is that if I do that, my du is going to be 1 over x dx. And I don't exactly have that. I should be careful here. Right, I have, you could write this as the integral of natural log of x over x cubed times 1 over x dx. And that could be your du, and there's your u, but you still have this x cubed left over, which is problematic. So it's not a u. I mean, you could do u sub and replace this x cubed with like e to the u, but then it's in integration by parts. I'm making sense. Anyway, instead, we're going to make the same choice, but we're going to do integration by parts. Meaning, if we're doing integration by parts, and we're thinking about the LIATE acronym, this is how we choose our u thing. We have a logarithm, so that should be our choice for u. And then your dv is everything else. I feel like I've kind of written this in the wrong order. I feel like usually when I'm writing integration by parts, I write u and then I write my du below it. So I would say du is 1 over x dx. My dv is everything else. So I've got natural log of x. dv is my 1 over x to the 4th dx. Or if you prefer, x to the negative 4th dx. And the antiderivative of x to the negative 4th is x to the negative 3rd divided by negative 3. Okay, so then we're going to integrate this. Now, I personally don't love carrying limits of integration with me. So I might do the following. I might say the integral of natural log of x over x to the fourth dx, the indefinite integral, is equal to that times that. So I might write that as natural log of x times -1 over 3x cubed, right? Bringing the x to the negative third down to the bottom, minus the integral of v du. So x to the negative third over -3 times 1 over x dx. The whole idea is to simplify this. So we're ending up with negative natural log of x over 3x cubed, just bringing that together. Minus a minus is plus 1/3. I bring out the 1/3 constant. And then x to the negative third divided by x is x to the negative fourth. Right? Because it's this power minus that power, and -3 minus 1 is -4. So integrating, we still have the negative natural log of x over 3x cubed. We get 1/3 x to the negative third divided by -3, which I would probably write as the negative natural log of x over 3x cubed minus 1 over 9x to the third. Right, I like my powers positive if I'm going to have to evaluate this thing. So then I'm going to plug in my limits of integration, which were probably poorly chosen. So here's what I would do. I would probably then write something like, I would leave this work shown, but I need the room. So then I'd say, okay, if my indefinite integral is equal to that, and my definite integral is equal to that, evaluated between 1 and 7 seems like a very poor choice. Let's make that a 10 just to make it not quite so ugly. Sorry. So plugging that in, you're going to get the negative natural log of 10 over 3 times 10 cubed. That's easy to calculate. That's 3,000. There's not enough room. Sorry. This is equal to plugging in 10, negative natural log of 10 over 3 times 1,000, so 3,000, minus 1 over 9 times 1,000, minus negative natural log of 1 over 3. Oh, that's 0. And then minus 1 over 9. So not doing too much more simplifying here. I'm getting negative natural log of 10 over 3,000 minus 1 over 9,000 plus 1/9. Yes, you can get a common denominator. I guess we could get a common denominator, fine. This is equal to 9,000 to my common denominator. Multiply this by 3 over 3. Multiply this by nothing. Multiply this by 1,000 over 1,000. So that's how you can write your final line. So that part's not that important though. So yeah, but if I have a definite integral and I have to use integration by parts, I personally think it's a good idea to do the integration by parts with the indefinite integral, do all your work, get your antiderivative, and then go back to the definite integral, say, okay, it's equal to the antiderivative you found down there, evaluate it between your limits of integration, and then do the work. I think that's just going to be, it's usually a nicer way to kind of keep, it's better than like, I think it's better than doing this, right? In each step saying, okay, this is the integral from 1 to 10, and it's this from 1 to 10, and this from 1 to 10, and so then it's this from 1, right? This just feels messy to me. You might disagree. You should do whatever's best for you. All right, let me go to the next one. Someone's asked. I have number 6 from practice problems, from her practice problems. Okay. Let's see. Yeah, it's a good problem. And then I have number 4 from homework 4, number 6. What's homework 4? Is that like from her assignments, I'm guessing? I'll get to that in a minute. So here's number 6 from our practice, and we want to find the derivative of h of x equal to the integral from, okay, sorry, I lost my spot, 2 to 1 over x of the arc tangent of t dt. So the whole idea with this, right, if you're trying to find the derivative, when you're finding the derivative of the integral, in fact, right, so if this was just an x instead of a 1 over x, the answer would be the arc tangent of x, because the derivative of the antiderivative of the function is just the function. But when this is more complicated, there's a little extra steps. So the derivative here is going to be, it's going to be the arc tangent of 1 over x plugged in for t. But then we have to multiply by the derivative of 1 over x. And the derivative of 1 over x is well, right, it's x to the negative first. The derivative is negative x to the negative second, or negative 1 over x squared. So that's your derivative. So whenever you're differentiating the integral of a function, you're just getting the same function, but if your limit of integration is some function of x that's more complicated than just x, you're plugging that in, and then you're also multiplying by its derivative. So if I said my function was instead, say, g of x was equal to the integral from 1 to 3x of the arc tangent of x, then g prime of x would be the arc, this would be arc tangent of t dt. Sorry about that. Then the derivative would be the arc tangent of 3x times the derivative of 3x, which is 3. So that's always kind of the gist. I mean, the derivative of the integral. Okay, let me look at homework number 4 real quick here. One second, I did not have the homeworks up. Corona 17B. And then I'll get to the next question after that, which is about a differential equation. Yeah. Let's see, homework 4. Yeah, let me see homework 4. Let's see. Problem 6 and 4. Okay, totally. So problem 6. Okay, and 4. Okay, yeah. Oh, what problem? The problem I just did was number, so this one I made up, but this problem was number 6 from her practice review, or review, her final review, whatever it's called, from Karana's final exam prep optional worksheet. That's what that was. It was problem 6 from that. Okay. Let's take a look at, so let's see. So let's look at number 6 first. So 6, and there's 2 parts to each of these. So it's the integral of sub x squared times sine 2x. This is definitely looking like an integration by parts problem. And I know that light tells me, right? I don't have any logs, I don't have any inverse trig, but I do have an algebraic term or an any power of x term. So this is going to be my u, this is going to be my dv. You could use tabular here. If this is an instance where you can use tabular, because it's a power of x times, I should say a positive integer power of x times a trig function. But I'm not going to do that just because I don't know if everyone remembers it. Yeah. Welcome to whoever just came in. Here's the attendance form. Please fill it out when you have a second. I'm currently working on this problem from homework number 4. It's problem 6. So let's see. So we're letting u equals 7x squared. Our du is 14x dx. Our dv is sine of 2x dx. And the antiderivative sine of 2x dx is negative cosine of 2x divided by 2. Okay, so then this integral is equal to u times v, so 7x squared times negative cosine of 2x over 2, minus the integral of v du, so negative cosine of 2x over 2 times 14x dx. And I do think it's worthwhile to cancel a 2 here and a 2 here. I'm going to do a little bit of simplifying. I'm going to write this as negative 7/2 x squared times cosine of 2x. Minus a minus is plus. And write this as 7x, integral of 7x times cosine of 2x. And I think for integration by parts, it's actually kind of not in our benefit to factor out, to bring out this constant term. Because when you do that, you have a 7 out here, and that 7 has to multiply by everything this integral is equal to, which is kind of 2 pieces because it's integration by parts. So I think you're actually better off leaving that constant term with either the u or the dv. So for my second integration by parts step, so that was my first step. Here's my second integration by parts step. For this integral here, I'm going to let u equal 7x and dv equal cosine of 2x dx. So if u is 7x, du is 7 dx, and then dv is cosine of 2x dx, and the antiderivative of that is sine of 2x over 2. All right, so now our answer is going to be, we still have this piece here, this negative 7/2 x squared cosine of 2x, plus, now for this integral, we're going to do integration by parts, so uv minus the integral of v du. So uv is going to be, let's actually say it's going to be 7/2, and then it's going to be x times sine of 2x. Okay, and then, and then minus the integral of v du, which will be 7/2 times sine of 2x. I'm feeling a little bit lazy here. I'm just going to do the integral of this. So the integral of 7/2 sine of 2x is going to be 7/2 times negative cosine of 2x over 2. Sorry, so this is going to be minus negative 7/2 cosine of 2x divided by 2. So this part would turn into plus 7/4 cosine of 2x. Hopefully everyone's okay with that. Okay, let me erase the other side here. So we're still looking at homework 4. Let's look at 6. The other part of problem 6. Which hopefully is maybe less terrible. Maybe not. Oh, it's okay. If I had to guess, I would guess she probably wouldn't ask one like this. Doesn't mean I won't do it, but this feels, I don't know. I guess it's not totally out of the realm of possibility. So the integral x to the 5th e to the negative x squared over 2 dx. So this is probably one of those problems where you have to do a u sub and integration by parts. I'm not exactly sure, but I know that, well, here's what I do know. I know that I don't know how to integrate e to the negative x squared. In fact, it's impossible to integrate e to the negative x squared over 2. So we know that this can't be a dv because we can't integrate that and get v. So I know I can't start off by doing integration by parts. I'm probably going to try a u sub. I'm going to let u equal negative x squared over 2. And then du is equal to negative 2x over 2, so negative x dx. So negative du equals x dx. And I can write this as the integral of x to the 4th times e to the negative x squared over 2 times x dx, right? My x to the 4th times x is my x to the 5th. And the reason I broke off an x was I would have x dx. So that right there is my negative du. This here is my e to the u. And this here, well, I can solve this for x squared. I can multiply both sides by 2. So 2u equals negative x squared, and then negative 2u equals positive x squared. So that x to the 4th is x squared squared. So that's going to be negative 2u quantity squared. All right. This is a terrible problem. So then we're going to end up with the integral of 4u squared e to the u times negative du. Or negative 4 times the integral of u squared e to the u du. And this one is integrated by parts twice. The terrible thing here is I used u before I had to do integration by parts. So for my integration by parts, I'm going to use w and v instead of u and v. And now I'm going to erase this. Oh, except fine. I'll keep this right here. I'll keep that up there. So for my integration by parts, I'm going to let my w be u squared. My dw is 2u. My dv is e to the u, and my v is e to the u. So rewriting my integral, it's negative 4 times wv, u squared e to the u, minus the integral of v dw, so e to the u times 2u. And then we have to do it again. So we're going to have, let's see. So now in this integral, our w is 2u, our dw is 2, our dv is once again e to the u, and our v is e to the u. So then we're going to get negative 4 times u squared e to the u minus, so the integral of this is going to be wv, so 2u e to the u, minus the integral of v dw, so 2 e to the u. It's getting messy. All right, so here's what we've got. Yeah, I wish I had more room. Yeah, I'm going to erase some stuff, sorry. I guess I'll go to the other side. So we've got negative 4 times u squared e to the u minus parentheses 2u e to the u minus the integral of 2e to the u, which is 2e to the u. Okay, simplifying this a bit. So it's negative 4 times all of this. So it's negative 4 u squared e to the u. And negative 4 times negative this is plus 4 times all this. So it looks like I've got negative 4 u squared e to the u plus 8 u e to the u minus 8 e to the u. And then to finish the problem, we have to go back and plug in that u is e to the negative x squared over 2, which seems dumb. So we've got negative 4 times e to the negative x squared over 2 times e to the negative x squared over 2. That seems wrong. That seems like I'm making an idiotic mistake. And I am. So I wrote down the wrong thing because I erased and then didn't remember. U is just negative x squared over 2, not e to the negative x squared over 2. So we really have negative 4 times negative x squared over 2 squared e to the negative x squared over 2 plus 8 times negative x squared over 2 e to the negative x squared over 2 minus 8 e to the negative x squared over 2 plus c. Okay, that's terrible. I would be really surprised if she asked something that awful, because u sub and integration of parts twice just seems like kind of a lot. Okay, let's look at problem 4, which is more of the same. I think so. I'll come back to problem 4, but let me skip to some other things so we can kind of break it up a little bit. So let me look at the problems that a couple other people asked me to do. Sure, yeah. So next on deck is the differential equation dy dx equal to 2x cubed over y with y of 1 over 3. y1 equal to 3. And then I have another problem, and then someone just asked for problem 7. Okay, yeah, we're good. We're good to go. Keep the questions coming. It's good to have questions that are source material. So let's see here. Sorry, I just lost my spot. Okay, cool. Good. I didn't want to do number 4. It looked painful. We can the second part looks painful. The first part probably not so bad. But if we run out of things to do, we'll come back to problem 4. So we want to solve this differential equation: dy dx is equal to 2x cubed over y. And we know that y of 1 equals 3. And we're also supposed to assume that both x and y are greater than 0. Just a point that I noticed that on her final review, whatever it's called, I did not see on her final review, final exam prep optional worksheet, I did not see any of the integrating factor type of differential equations. I don't know if that was on purpose or if it was an oversight, but if I was looking at that, it would make me think there probably won't be any integrating factor problems on your final. I don't know if she said anything about that, but that is kind of what it would make me. I might spend less time practicing that specific thing if I didn't see any of them on her final review. You might ask her. The problem with asking her is it might be like, oh, I didn't think about that. So I don't think she'd really do that. Like I think she's probably already got her final pretty set. But if you were concerned about an integrating factor problem, you might ask her if that could show up on your final. I don't know. I don't want to ask her because I don't want to be like, oh yeah, by the way, you didn't think of this. So yeah. So yeah, let's solve this one. So this one definitely is not an integrating factor problem. It is for sure gosh, what do you call it? Separable. It's a separable differential equation. Sorry, the words are starting to fail me. So we're going to bring all the y's to the left, all the x's to the right. So we're going to have multiply both sides by y, multiply both sides by dx. We got y dy equal 2x cubed dx, 2x cubed dx. Yeah. Integrate both sides. Y squared over 2 equals 2x to the 4th over 4 plus c. And this is why it's important that we say that both y and x are positive, because technically y could be positive or negative and x could be positive or negative, and you could still have this have solutions because something squared and something to the 4th are always positive. So it is worth noting that yes, x and y are positive, especially when we solve this. So solving this, and do we want to find c now? I don't know, probably not. I might at least multiply both sides by 2 first. So I'm going to say that y squared equals, yeah, it's going to be nice. Multiply this by 2, you're going to get x to the 4th plus 2c, which I'm going to call c again. Or if you want, you can call this one c1 and this one c2. You don't really need to though. Right? This is much nicer to plug into than this. So here, I'm going to get y, which is 3 squared equal to 1 to the 4th plus c2. So 9 minus 1 is equal to c2. So this is probably the best. I mean, you could go further, but so then we've got y squared equal to x to the 4th plus c2, which is 8. And then solving for y, you get, so you don't get plus or minus. Right? It's not plus or minus the square root of x to the fourth plus 8. Specifically because we said, oh yeah, x and y are both positive. So y can't be negative. It's only the positive square root of x to the fourth plus 8. So that is our final answer. Y equals the square root of x to the fourth plus 8. That's a good question. All right. So next one up is problem 2, part B from short test 1. Let me grab that real quick. Short test 1. Okay. Problem 2, part B. First short test, problem 2, part B. Okay. Okay, sure. Yeah. So I'm going to do this one both the long and the short way, just to kind of show you how it works. So problem 2, part B. We're given the following. Suppose the sum from I equals 1 to, there might not be a long way to do this. That might just be crazy. Suppose that that's equal to 3. So I don't know what that is, right? I don't know what each of these are. A1, A2, A3, all the way to A sub 9. But I know when I add them up, it equals 3. They could all be different, right? This could be, I don't know. I don't really want it, but it could be like 0, 1, 2, 3, -2, something, something, something. So it adds up to 3, right? It could be totally crazy numbers. But then the question is, I want to know what this is. The sum from I equals 1 to 9 of 7/3 minus A sub I. Okay, actually, so I can't do this one both a long and a short way. So let me show you the long way. I'm going to add it up. This is 7/3 minus A1 plus 7/3 minus A2 plus 7/3 minus A3 plus all the way to the very last term, which is 7/3 minus A sub 9. Okay, so let me ask you guys, how many, well, let's see, there's A1, A2, A3, all the way to A9. How many instances of 7/3 are there? How many 7/3 am I adding up together?
9.
Right. So I've got 9 times 7/3. And then I've also got minus A1 plus A2 plus A3 plus all the way to A9. Right, I factored out the minus sign. All right, it's a negative A1 plus a negative A2 plus a negative A3, which is all that. Where does the 7 come from? So the 7, so the only 7 I think you're talking about is this one right here. So we were given this, the sum from I equals 1 to 9 of A sub I, and then we were asked to find this, the sum from I equals 1 to 9 of 7/3 minus A sub I. Does that clear things up? Okay, cool. Yeah, it didn't come from anywhere except for, it came from the imagination of Dr. Brooke, right? Like she's like, I'm gonna make 7/3. Okay. So then 9 times 7/3, we can cancel a 3. And 3 times 7 is 21. Minus, we know this adds up to 3, because we were told it added up to 3. So our final answer is 18. Okay, so that's the long way to do this. Here's the short way to do it. The short way to do it is to use the properties of summations. And say, well, if you have a sum of a difference or a sum, you can break it up. You can write that as the sum from I equals 1 to 9 of 7/3 minus the sum from I equals 1 to 9 of A sub I. Now, when you're adding up a constant, you just get the number of times that constant. Well, there are 9 7/3 being added up here, just like we saw up here. So that's going to be 9 times 7/3. Minus, we know this thing, that's equal to 3. So we get the same thing we got there. We get 21 minus 3, which is 18.
Here you don't have to multiply the a sub 1, or like, so it would be 3 times the 9 though?
No.
Like, is that saying that's all together already?
So say that one more time.
Oh no, I already realized what I.
Okay.
Yeah.
All right. Someone asked for problem 7 from our practice problems. Okay. Let's look at that. Oh yeah, cool. So integral of 1 over x times x plus 1. So I don't see a good u sub here. I don't see integration by parts. I usually integration by parts, there has to be some other kind of like a logarithm or an exponential or a trig function. But here we just have x's, right? We don't have any other functions other than like 1 over x, 1 over x plus 1. This is definitely looking like partial fractions. Because I see that one, I have a fraction, a rational function. Degree on top is less than the degree on the bottom. The degree on top is 0. The degree on the bottom is 2. And more importantly, well, but as importantly, the denominator factors. So I'm going to write this as, I'm going to do the partial fraction decomposition. And say that this is equal to a over x plus b over x plus 1. Doesn't matter which order you do it. You could just like a over x plus 1 plus b over x. Doesn't matter. And then we're going to multiply both sides by the common denominator. So we're multiplying both sides of this equation by x times x plus 1. When you multiply it here, you just get the top. When you multiply it here, the x's cancel and you get a times x plus 1. When you multiply it here, the x plus 1's cancel and you get b times x. Now, there's a lot of ways you could do this. I'm going to show you both, or I'm going to show you 2 ways. The way I would encourage you all to do it is to pick what I call the convenient values of x, meaning the values of x that make one of those or more things become 0. So if I pick x equal to -1, -1 plus 1 is 0. So in fact, let me get a little more. Yeah, sure, fine. I just don't want you to miss this one here. So I pick x equal to -1. I have 1 on the left. I have a times 0 plus b times -1. So I have 1 equal to -b or -1 equal to positive b. I pick x equal to 0, then this part's going to go away. I'll have 1 on the left equal to a times 1 plus b times 0. That goes away, just like that went away, and you get a equal to 1. And that's the way I think is the easiest way to do it, as long as things go away. She might, I don't know, just to kind of talk about how she would solve this, she would probably do it like, she would say 1 equals ax plus a plus bx. And then she would combine like terms. So ax plus bx is a plus b times x plus a. On the left, I have 0 x's. So 0x plus 1 equals a plus bx plus a. And the like terms have to be the same. So a here has to equal the constant term here. So a has to equal 1. And then a plus b here, the coefficient of x, has to equal the coefficient of x there. So a plus b has to equal 0. But knowing that a equals 1, 1 plus b equals 0, so b equals -1. Same results. Either way of doing it is fine. You should do whatever you're comfortable with. So then we're back to the integral, right? So that's the important thing to remember. When you do partial fractions, you'll have done the partial fraction decomposition. You'll have found a and b or c, right? However many things there are to find. But then you have to go back and say, oh, this thing here, right? This integral is equal to the integral of, well, 1 over x times x plus 1 is equal to 1 over x minus 1 over x plus 1. And then you actually have to do the integral. which is usually easy. So the integral of 1 over x minus 1 over x plus 1 is the natural log of the absolute value of x minus the natural log of the absolute value of x plus 1 plus c. And just because it's kind of important, and it definitely did come up in one of the questions that I asked on my practice final, sometimes it's really important that you compress this into one natural log and write this as the natural log of the absolute value of x over x plus 1 plus c. Okay, I'm going to take a 3-minute bathroom break. I'm going to fill up my water. I'm going to come back. More questions. All right, we'll get started back in just a moment here.
I had a quick question about the problem that we just did.
Yeah.
So at the end, why is how is it possible to combine the two lns together?
So there's this rule about logarithms that in general, if you have, doesn't matter what the base is, so if you have the natural log of x plus the natural log of y, as long as the bases are the same, that's the natural log of x times y. And if you have subtraction, the natural log of x minus the natural log of y is the natural log of x divided by y. So that's the rule I'm using, is that since I have a logarithm subtracting another logarithm, I can divide their arguments.
Okay, that makes sense. And then I had another quick question.
Sure.
You wrote when we were doing the integration by parts, LIATE. Could you explain what that stands for?
Sure. So when you're doing, in fact, let's actually, since no one else has any other questions on deck, let me go back to problem 4 from the homework, and I'll explain it as we go along here. So let's look at this one. So these are both definite. I'm going to do them indefinitely first. So and if the integral from 1 to 4 of e to the square root of x plus 2 dx. I'm going to choose first to just look at the indefinite integral, e to the square root of x plus 2. And I'm going to make the choice to make a u substitution. I'm going to let u equal the square root of x plus 2. Which might seem kind of weird. So here's the thing I'm going to do this time though. Since I know the problem says it's a u sub followed by integration by parts, I'm going to not use my u up. I'm going to call it t. Say t is the square root of x plus 2. And this one's a little tricky. So there's a couple ways to do this. So this is t equal to x plus 2 to the 1/2. Your dt is 1/2 x plus 2 to the negative 1/2 dx. So your dt is 1/2 times the square root of x plus 2 dx. So the thing is, I have e to the t, but I don't know how to deal with this dx. The issue here is that I can actually solve this for dx and say, okay, dx is equal to 2 times the square root of x plus 2 dt, but the square root of x plus 2 is your t. So that dx is equal to 2t dt. So this integral is equal to the integral of e to the t times 2t dt. All right, and now we're going to do integration by parts. So here's the thing, and let me go to the other side to happen. So if we're doing integration by parts, which is again, I've got 2t times e to the t dt. There's kind of a method for picking your u. So how do we pick u? Well, first we look to see if there's any logarithms. There aren't. So I'm not going to pick u equal to a logarithm. Then we look to see if there's any inverse trig, like an inverse sine, inverse cosine, arctangent, anything like that. If there was, I would pick that for you. There isn't. Then we look for any, so some people call it an algebraic term, or I like to say any power of your variable. Oh, well, I do see that. I see 2 times t to the first. If I didn't, I would then look for a trig. I don't see any sine of t or cosine of t. And then you almost never pick u to be an exponential, meaning e to the something. I should just write that. E to the something. So I'm going to pick my u equal to my any power. And I might as well bring along the constant for the ride. So I'm going to let u equal 2t. And then for integration by parts, once you know what your u is, you automatically know that dv is everything else. So my u is 2t. My du is the derivative of 2t, which is 2 times dt. My dv is e to the t dt, and my v is just e to the t. So then we can say that this integral is equal to u times v minus the integral of v du. And then we can integrate that. We still have the 2t e to the t minus the integral of 2 times e to the t is just 2 times e to the t. I'm not going to throw on a plus c here because I know that I'm just trying to answer a definite integral on the other side. So that's my integral. Let's go back to the other side. So this is equal to 2t e to the t minus 2 e to the t. But then we have to go back and plug in, well, no, yeah. I would go back and plug it in and say that this is equal to 2 times the square root of x plus 2 times e to the square root of x plus 2 minus, you know what I might actually do? If I was trying to make my life a tiny bit easier, which I should be, I should factor out a 2e to the t. This is 2e to the t times t minus 2. And then you can plug in what t is, which is 2e to the square root of x plus 2 times the square root of x plus 2 minus 2. So then finally, if you actually want to answer this question, it's equal to, so our antiderivative is that, it's kind of terrible. So that's equal to that antiderivative evaluated from 1 to 4. So you plug in 4, you get 2e to the square root of 6 times the square root of 6 minus 2, minus you plug in 1, you get 2e to the square root of 3 times the square root of 3 minus 2. It's a gross problem. But to answer your question very, very longly, the whole idea with this Lie thing is it's the order in which, if you think the problem is integration by parts, it's the order you try picking what your U thing is. Let's see. So someone else has asked problem 11 from the practice final thing from Burke. Oh yeah, it's a good question. I would be pretty surprised if she didn't ask you something like this on your test. It just seems like this type of problem. Not the one we just did, the one I'm about to do. I would bet that a problem like this will probably show up on your test. It seems pretty reasonable. So here's the problem. We want to that's still fair. We want to solve dy dx equal to 2y times 3 minus y. And we actually do want to solve it. I'm going to talk about answering the second half of it without solving it. With y not equal to 5 when x not equal to 1. Which I would personally write as y of 1 equal to 5. But that's fine. So I just want to point out, the second part of this question asks, what happens as x goes to infinity? And that is something we can actually answer with the phase plot and without solving it. So I'm gonna show you that first, and then we'll solve this and see how we didn't actually have to do that. But so if I want to ask what happens as x goes to infinity, well, I'm going to draw the phase plot for this. dy dx on the vertical axis, y on the horizontal. My equilibria are the things that make this equal to 0. So y equals 0 and y equals 3. And then to see if it's positive or negative, pick a point like 1. I plug in 1, I get 2 times 2, which is 4. So I know it goes like this, and then like this. Okay, so here's what I know. I know that in this region from 0 to 3, my derivative is positive, right? My dy dx is above the horizontal axis, which means y is increasing. And over here to the right, my derivative is negative, which means y is decreasing. Which means not that they've asked us this, but it means that 3 is a stable equilibria. And 0 is unstable. Okay. So then, if I want to ask what happens as x goes to infinity, well, look, I know that when x is equal to 1, y is equal to 5. So the beginning point, I'm starting right there. Right? When x is equal to 1, y is equal to 5. I can't, right, this graph doesn't have anywhere to plot the x's. All I can plot is the y's versus the derivatives. So technically, I'm not really starting here, right? I'm actually technically starting down here, right? Because when x is equal to 1, y is equal to 5, and dy dx is equal to whatever it is equal to. But I really only care about the behavior of y, which is really just plotting it right there. So then what happens as x goes to infinity? Well, as x goes to infinity, from starting here, dy dx is negative, which means y is getting smaller, which means we go that way. So we can answer the question, what happens as x goes to infinity? Y goes to 3 is the answer to that question. As x goes to infinity, y goes to 3, or the limit as x goes to infinity is equal to 3. I should really say the limit as x goes to infinity of y as a function of x is 3. We will also see that when we solve this, but you can totally answer limit questions if you know an initial condition by drawing the phase plot, which is kind of cool. Okay, well, let's actually answer the question. And then we'll do whatever, I think someone asked for number 23 or something. We'll do that one next. So let's see. We're trying to answer the question. Dy dx equal to 2y times 3 minus y. So again, separating our variables, divide both sides by y times 3 minus y. So 1 over y times 3 minus y equals 2 times dx. I don't forget the dy over here, sorry. Integrate both sides. Partial fractions. So 1 over 3 times 3 minus y. 1 over y times 3 minus y equals a over y plus b over 3 minus y. Multiply both sides with the common denominator. You get 1 on the left. You get a times 3 minus y plus b times y on the right. Set y equal to 3. You get 1 equal to a times 0 plus b times 3. So that's going to be b is equal to 1/3. And then for y equal to 0, you're going to get 1 equal to a times 3. So a will also equal 1/3. So this integral on the left will be the integral of 1/3 over y plus 1/3 over 3 minus y equal to, I can integrate this on the left, on the right, and get 2x plus c. One nice thing about when your a and your b values are the same or opposite values, like one's positive, one's negative, is you can totally factor that out. And you can totally factor out the 1/3. And then you can say, okay, this left side is going to be 1/3. Now we have to be extra careful here. It really, really matters. The integral of 1 over y is the natural log of the absolute value of y. The integral of 1 over 3 minus y is negative natural log of the absolute value of 3 minus y. And right, we need that negative, right? Because, right, the derivative of the natural log of 3 minus y is 1 over 3 minus y times -1. But I don't have that -1 here, so I need a negative to counteract it. Okay, and what we know that y of 1 equals 5, right? Or x naught equals 1, y naught equals 5. I think that was right? Yeah. Okay. So to solve this, we have to be kind of extra careful. Let's multiply both sides by 3. And we have to combine these logarithms. That's kind of the key step here. Is that this is the natural log of y over 3 minus y. And yes, I'm ignoring the absolute value sign because it's pretty safe to do so. If you want, this is C1, this is C2. We don't really usually worry about that. We just call it both C. Okay, now we're going to exponentiate both sides. I'm going to erase this unless there's, are there any questions about this before I erase this? Okay. So I'm going to do e to the this. So I'm going to get y over 3 minus y equal to e to the all this. It's going to be e to the 6x times e to the c2, which I'm just going to call c3. PO. Okay. Anyway, so then really what we're going to do is we're just going to flip both sides over. So you can say that, yeah, how do I want to do this? The algebra here does get a little bit messy. I won't lie. Does it make sense to plug in? No, it really doesn't make sense to plug in yet. You really don't want to solve for this until like kind of the very end. Right, so we know that again, right, we've got x equal to 1, y equal to 5. Okay, so let's see what we've got here. Yeah, if I multiply both sides by 3 minus y, so y equals c3 e to the 6x times 3 minus y. Distribute y equals 3c3 e to the 6x minus c3 e to the 6x times y. And then bring that over there. So y plus c3 e to the 6x times y equals 3c3 e to the 6x. Finally, factor out the y. Okay, factor out the y. So I'm going to factor out the y. So it's y times 1 plus c3 e to the 6x. And then divide by that. So y equals 3c3 e to the 6x over 1 plus c3 e to the 6x. The reason I didn't multiply the 3, but the reason I didn't say like 3 times c3 was a new constant was because I've got c3 showing up twice now, so that might not be safe to do that. All right, so now at this point, I'm going to solve for my constant. So I'm going to plug in 1 for x and 5 for y. So maybe, okay, so watch, and then we will all learn something together. By plugging 5 for y here and 1 for x here, it looks like solving for C3 is going to be kind of stupid. Like maybe I should go back to right here where you've almost got C3 all by itself and solve for C3 there. So it's okay to wait, but if you see that doing it like at a later point is going to be terrible, go back to a place where it looks like basically you're undoing the work you just did. So yeah, I'm going to erase this. So plugging in 5 for y. Interesting. Equal to e to the 6 times c3. So let's see, we're going to get c3 equal to 5 over -2, so -5 over 2e to the 6th. Crazy. So that's kind of a terrible pain. Maybe not so much. So if we plug that in, let's see what we get. Sorry, I know I've got. So I'm going to get this up here. Sorry, try to keep track of everything. So C3 is -5 halves. So I plug that in, look what I get. You get y equals this 3 times -5 over 2 e to the 6th times e to the 6x over 1 plus -5 over 2 e to the 6 e to the 6x, which, okay, feels kind of dumb, but you can simplify it a little bit. 3 times -5 halves is -15 over 2. E to the 6x divided by e to the 6 is e to the 6x minus 6 divided by 1 minus 5 halves e to the 6x minus 6. Often people would multiply this by 2 over 2 to get -15 over 2 minus 5 e to the 6x. Okay. You can double check that your value is right? If you plug in 1 for x, you get e to the 0 and e to the 0, and then you get -15 over, I think I made a mistake. Oh, no, I'm just crazy. You get -15 over 2 minus 5, which is -15 over -3, which is positive 5. All right, so then the question, oh yeah, so cool. So then the question, what happens as x goes to infinity? Well, as x goes to infinity, this gets really, really big. This also gets really, really big. They get big at the same rate. They're literally the same thing. So basically, these terms dominate. This becomes inconsequential, and you get something that's negative 15 over negative 5, which is positive 3. Positive 3. So it seems like it's way easier to find the limit doing it this way, right? The other way was still a lot of work, but you can do it this other way. I mean, the other way, you also find the solution to the differential equation, which is also interesting. But right, let me just point out, in case it's not clear what I'm saying, that if you were asking what the limit of this was, the limit as x goes to infinity of negative 15, I would probably multiply the top and bottom by negative 1. Right, this is positive 15 e to the 6x minus 6 over 5 e to the 6x minus 6 minus 2, right? That just seems a little bit nicer. Then if you divide the top and bottom by e to the 6x minus 6, this is 15 over 5 minus 2 over e to the 6x minus 6. And then hopefully you guys can see that as x gets really, really big, this gets really, really big, this gets really, really small. So you get 15 over 5, which is 3. It's a bit of work. So definitely right. I know I erased most of my work here, but solving this sort of algebra can be fairly challenging. Right? You have to, when you have y over 3 minus y equal to e to the this, you then have to, right? It's really, really important when you get to this step, y over 3 minus y equal to e to the 6x times e to the c2, which I called c3. But then you have to multiply both sides by this and then distribute and then isolate your y's and so on and so forth. Okay. It's a good one. Let's look at the next one. That was problem 11. Sorry, 1 second. Sorry, 1 moment. So let's look at 23. It's got a lot of problems on this practice final. 23. I looked at this one. I didn't look at this one close enough. So this one might, I might need to, let's take a look here. So many species are made up of several small subpopulations that occasionally go extinct go extinct. I'm not sure if the words there seem not right. Small subpopulations that occasionally go extinct by that are subsequently recolonized. There's something missing there. It's fine. The entire collection of subpopulations is referred to as a metapopulation. One way to model this phenomenon is to keep track of only the fraction of subpopulations that are currently not extinct. Suppose, okay, so let's start writing some stuff down. So suppose that P of t obeys the differential equation. Oh, sorry. Suppose that P of t is the fraction of subpopulations that are not extinct. So P of t equals fraction of subpopulations not extinct. And I think it should make sense, right, that P of t should be between 0 and 1. Maybe with equal signs, right? Maybe 0 of them can actually be not extinct. That seems reasonable. But if 100% of them were extinct, it seems like they'd all be extinct. So I guess that's possible too. I don't know. But it's good to think about what parameters there are for your thing. So then, suppose Levin's model. So the Levin's model states that P of t obeys the following differential equation: dp dt is equal to c times p times 1 minus p minus mp. Okay. So just before even going further, right, we know what P is supposed to be, but we don't know what C and M are. So we have to think about what those are. What would be this? So C and M are both positive constants. C and M are both greater than 0. And C reflects the colonization rate, I assume, for C for colonization, and M represents the extinction rate, I would guess. C is the colonization rate. Because that's what I'm going to assume. I don't know why you wouldn't use E for this, but whatever. M is the extinction. Maybe it's like the murder rate. That sounds okay. That type of M is the extinction rate. The mortality rate. That's mortality rate. I don't know. Anyway, so assume that they are not equal to each other. C is not equal to M. First question. What are the equilibria of this model in terms of the constants? So we want to set this equal to 0 and solve for P in terms of C and M. So, right, in terms of the constants means our answer is going to have C and M in it. So I see that I can factor out a P from both of these. So P times C times 1 minus P minus M equals 0. So I either get P equal to 0. It seems reasonable that can be an equilibrium, right? If the fraction subpopulations that are not extinct is 0, that means all the subpopulations are extinct, right? The fractions that are not extinct is 0, that means 100% are extinct. If they're all extinct, you can't make any more of them, so that's an equilibrium. That seems like a reasonable equilibrium. And then we also have this, C times 1 minus P minus M equals 0. Let's multiply the C through, so C minus CP minus M equals 0. Let's add CP over here, so C minus M equals CP. Divide both sides by C. So P equals C minus M over C, or if you prefer, P equals C divided by C is 1, and M divided by C is M divided by C. Either way should be a fine way of writing. So those are my two equilibria, 0 and 1 minus M over C. Okay, so that's the answer to part A. Part B, what is the condition on the constants for the non-zero equilibrium? So by the way, reading this question tells me something about part A. It tells me I should have probably gotten 2 answers at least, right? Because it's asking me what is the condition on the constants for the non-zero equilibrium. So it says there's an equilibrium that's not 0, and it means that there probably also is one that's 0. Otherwise, I wouldn't have had to clarify that there was a non-zero one, right? Compared to the 0, 1. So sometimes reading the next question can give you some information about the previous question, right? That tells me, oh, there's probably a 0 equilibrium and a non-zero equilibrium. I should go back and make sure I have that. So look for those context clues in your test, right? Sometimes something in the next question will give something away about the previous question. So let's see here. So what's the condition for on the non-zero one? So this one in part A to lie between 0 and 1. Okay, so let me read that again. What is the condition on the constants for non-zero to lie between 0 and 1? Okay, which is what we were kind of saying before, right? We were thinking about this before we even got there, but she is now saying, yeah, this P should be between 0 and 1. So 1 minus M over C should be between 0 and 1. And I'm not going to worry about if it's less than or less than or equal to. So I'm going to deal with these separately. Let's look at this one first. So if I add M over C to both sides, M over C is less than 1. And if I multiply both sides by C, by the way, notice that C is positive. So multiplying both sides by a positive number doesn't change the direction of the inequality. So M has to be less than C. Okay. Which kind of makes sense if you think about it, right? If you want to have like an equilibrium that's not everyone's dead, the colonization probably has to be bigger than the extinction rate. And then here we have 1 minus M over C is less than 1. subtracting 1 from both sides, negative m over c is less than 0. We're adding that to both sides, m over c is greater than 0. So it looks like m has to be positive, right? Because c could be anything, I guess, right? I feel like that's not enough. I feel like I've missed something there and I don't know what it is. Maybe we already have that condition. Yeah, so think about it this way. And let me ask you guys if you want to chime in. M over C. We know M is positive. We know C is positive. M divided by C is also positive. 1 minus a positive number has to be less than 1. So this second part here really is kind of a non-factor. We know that no matter what M and C are, as long as they're both positive, we're going to get that that part is true. So the only part that we really need to be true is that M has to be less than C, or that C has to be bigger than M. Basically so that, right, this fraction is smaller than 1, so that 1 minus it is still bigger than 0. So either way of writing it, that's fine. Notice also they say to assume that M is not equal to C, right? So we wouldn't say that M is less than or equal to C or greater than or equal to C. We specifically want it to be greater than, right, C to be greater than M. All right, let's look at part D. Set up an integral that would allow you to solve this differential equation. Okay, so sure, we can probably set this up. I think I can already set this at this point. So let's see. So if I want to solve this integral, I'm going to hope that it's integration by parts. I mean, the separation variables. So right, I've got dp dt. I'm going to factor out a p because I know it can. So I have p times c times 1 minus p minus m. Okay, they just said set it up. They didn't say to solve. So it looks like everything has to come down to the left. So 1 over p times c times 1 minus p minus m dp is equal to 1 dt. I think that's it. Right? That we can totally separate the variables this way. Right? All the p variables ended up on the left. All the time variables, which there aren't any because this is an autonomous equation, differential equation, ended up on the right. Right, but if you have a differential equation, it's just in terms of your top thing, you can essentially divide the whole entire equation over to the left. And you'll have dp over some function of p equal to constant dt. And that'll work as far as setting up the integral. Actually, integrating this is probably a giant thing. Oh, he says before he reads the next question, which is solve the differential equation. Okay, so let's see what we've got. Blah. Okay. I asked for it there by saying it was going to be terrible, but it's probably worthwhile. So let's see what we've got here. Yeah, and I'm gonna simplify this a little bit. So I've got integral of 1 over p times. So I'm gonna write this as c minus cp minus m. Okay, sure. Yeah. Yeah, okay, fine. I feel like there's a fair number of partial fractions problems on this practice final, or this, whatever you want to call it. It makes you think you might want to spend a tiny bit more time making sure you know how to do partial fractions, because it feels like there have been a good number of them on here. So the denominator factors, it's factored. So I'm going to write 1 over p times c minus cp minus m equal to a over p plus b over c minus cp minus m. Here's the nice thing about this. I know I erased it, but we know what values make this equal to 0, right? When we answered, part A of this question, what are the equilibria? We got P equal to 0. That made this part 0. And we also got P equal to, I literally forgot what it was. 1 minus M over C, I think. That sounds right. Yeah, that's what, yeah, right. That's right there. Yeah. So the nice thing about this is that those are the values that make each of the factors 0. That'll help us when we solve this. So multiply both sides by the common denominator. We get 1 equal to A times C minus CP minus M plus B times P. All right, let's pick the easy one first. P equal to 0. We get 1 equal to A times C minus 0 minus M plus 0. So A is 1 over C minus M. Great. And then picking P equal to the other value, which was 1 minus M over C. We end up with 1 equal to, this should be 0, but let's check to be sure. A times C minus C times 1 minus M over C minus M plus B times 1 minus M over C. Okay, this is A times C minus a minus is plus M minus M. Yep, that looks like a big old 0. Plus B times, I'm going to write this as C minus M over C. So that when I divide both sides by this, B is going to equal 1 over C minus M over C, which is C over C minus M. Okay, that's not as terrible as it could have been. So that means this integral, we have on the left, the integral of 1 over C minus M over P. Plus C over C minus M over blah. I'm going to write that as negative CP plus C minus M. CP equals T plus K. I'm using K instead of C because we've already used C, right? Okay, and this is getting a little terrible, such is life. I can make this a little nicer because I can definitely, from here, I can pull out a 1 over C minus M. So 1 over C minus M. And then I have the integral of 1 over P. And then I have the integral of C over negative CP plus C minus M. CP equals T plus K. All right, we're almost there, but I'm going to have to erase some stuff. So are you guys cool with me erasing this? I'll give you a minute to not erase it. Okay, I'm not hearing any protesting, so I'm going to erase. So let's see here. So you get 1 over C minus M. The integral of 1 over P is the natural log of the absolute value of P. I'm probably going to drop the absolute values, but hey. And the integral here, so you're going to get C times the natural log of absolute value of negative CP plus P minus M. Now that's not exactly right, but I'm going to fix it with you guys. Okay, so let me ask everybody. I'm sorry, that's a C, apologies. Negative CP plus C. If you were to differentiate this natural log of negative CP plus C minus M with respect to P, right, because P is the variable. The derivative of this natural log of some stuff would be 1 over negative CP plus C minus M, and then what we'd have to multiply by from the chain rule. Anybody? Anybody?
The derivative of the inside.
Sorry, say that one more time.
The derivative of the inside.
Right,
Like
which
you would. Oh. Negative p plus 1. Oh no. Oh yeah.
just negative c,
Okay.
because the variable is p, and the derivative is negative c times 1 plus 0 minus 0. So we have to divide this by a negative c, because the chain rule would make our derivative multiply by a negative c, which is great, because then that c and that c will cancel. So, okay, here's what we get. We get 1 over c minus m times the natural log of p minus the natural log of that. Well, hey, I can write that as the natural log of p over negative cp plus p, sorry, good God. That's c minus m equal to t plus k. And now we're back in the same situation we were in the last problem we did, where we have to solve this equation for p, right? Because it does say solve the differential equation. And we do not have an initial condition. Great. Okay. So solving this is also terrible, but it's the same kind of thing we did before. So let me go to the other side. Okay, so there's my equation. 1 over c minus m times the natural log of p over negative cp plus c minus m equals t plus k. Then you multiply by c, looks like the c minus m, the natural log of p over negative cp plus c minus m equals c minus m times t plus k. And then you would exponentiate both sides, so you have blah. You have p over negative cp plus c minus m equal to e to the this garbage. I will point out that t times c minus m we need to actually consider, right? That's t times a constant. T is a variable, but c minus m times k, I'm going to call that let's call that, I don't know, d. It's e to the d. And then e to the d is the new constant, let's call it a. So, I mean, things are a little out of hand here. So this is equal to a times e to the t times c minus m. This problem, this is definitely a bit much for an actual final exam. But then we would, sure, you can do reciprocal both sides, so negative cp plus c minus m over p equals the reciprocal of that. And you can multiply by p up here. And then you can bring your p's to the same side. So c minus m equals p over a e to the garbage plus cp. Finally, factor out a p. You're left with 1 over a e to the t times c minus m plus c equal to c minus m. And then finally, p is equal to c minus m divided by this hot trash, 1 over a e to the t times c minus m plus c. Good God, that's insane.